So this is problem 2.22 out of Griffiths, and we have to find the potential at distance S away from an infinitely long straight wire that carries uniform line charge lambda. So for this, we're going to need to find the E field. And I went ahead and draw the black line being the infinitely long straight wire, and then the green part is our Gaussian surface. And I drew that so we could use Gauss's law. So the closed surface integral of E dot dA is equal to the enclosed charge over epsilon naught. And the left-hand side, as usual, give us the magnitude of E times that surface area, which for a cylinder will be 2 pi L, in this case S, because that's our radius, is equal to our enclosed charge over epsilon naught. And we can think of the enclosed charge as being the integral of lambda dL, or just lambda L. And lambda has units charge, or we could think, I guess, of coulombs per, we'll just say meters, and L has units meters. So you end up getting units of charge, which is coulombs. So then we have the magnitude of our E field times 2 pi Ls is equal to lambda L over epsilon naught. You can see the L drops. And then our E field is equal to lambda divided by 2 pi epsilon naught S hat. So now we have the E field. What we want to do now is use that to find the potential. So delta V is equal to minus the integral of E dot dL. Now, we'll just say that it goes to S from, let's say, some point A. It doesn't really matter what, we'll call it that. Minus the integral from A to S, lambda over 2 pi epsilon naught S ds. So dl in this case would be S hat ds. So that's what's happening to our S hats here. The reason why we're not using infinity here is because it doesn't really work with the domain of the function we're going to get for our potential. It ends up kind of blowing up. So for that reason, we're just defining A as being your reference point, such that the potential there is 0. Whether that's infinity or whatever point you want it to be, it's just a matter of definition. So then our potential is going to be minus lambda, over 2 pi epsilon naught, the integral A to S of 1 over S ds, which will get us the natural log. So minus lambda over 2 pi epsilon naught, and that's a natural log of S over A. And I'll use absolute values because of the domain of our natural log function. And that's it. That's your potential there. So a little bit different with our reference point, really. We have to do Gauss's law to find the E field, and then we have to define the potential accordingly. So hopefully that makes sense.